Okay, let's unpack this. Imagine trying to design really complex electronics,
Yeah, intricate
like
stuff.
the sensitive detectors you find in satellites or, medical devices. Traditionally, this is just painstaking work.
Weeks of effort, easily.
Right, weeks of tweaking, trial and error, relying so much on, well, human expertise and intuition.
Mm-hmm.
Now, picture this. You just set the goal. You say, okay, I need a sensor that does this specific thing, hits this performance level, and then you let artificial intelligence figure out the design
Automatically.
automatically and much, much faster. That's really the aha moment in this fascinating paper you sent us. It dives deep into using AI for unsupervised design and optimization, specifically for microwave sensors.
And these aren't just abstract ideas. These sensors are critical components.
Absolutely. They're in everything from, say, checking moisture in crops.
All the way to advanced aerospace uses? Yeah.
So, our mission today is to guide you through this research. We'll pull out the key insights, the surprising facts, help you understand how AI is starting to, well, revolutionize how these high-performance devices get made.
So yeah, the key thing to get is what these sensors actually do. Microwave sensors fundamentally work by looking at how microwave signals interact with whatever they're aimed at.
A material, a liquid.
Right, or even just the air. They're sensing changes in properties, like how well something conducts electricity or stores it, or how it affects the electromagnetic field nearby.
And they really are everywhere once you start looking. The paper points out uses across, a huge range of fields: aerospace, agriculture, defense.
Food processing, biomedical sensing, detailed material
That's a
analysis.
surprisingly broad impact.
Definitely. And you've got different types. Broadly, you can think
Yeah.
of resonant and non-resonant techniques.
Okay.
Non-resonant can be faster sometimes, good for quick checks, maybe non-contact situations.
Sure.
But for applications where you need really high accuracy, high sensitivity,
Yeah.
resonant sensors are usually key.
And this paper zeroes in on those resonant sensors. They often use these special structures called metamaterials.
Exactly. Things like split ring resonators, SRRs, or their complementary versions, CSRRs.
These are like tiny patterns, right, etched onto circuit boards.
Precisely. Designed to resonate really strongly at specific microwave frequencies.
Yeah.
And they're popular because, well, they can do multiple things. They're small, cost-effective, versatile, easy to integrate.
And crucially, they help achieve high sensitivity, that ability to spot even tiny changes.
That's the main advantage for many applications.
So if they're so useful, what makes designing them the old way such a slog? Why weeks of expert time?
That's the core problem this research is tackling. The conventional way is fundamentally manual.
Great.
You start with some basic ideas, maybe combine some known components, and then you iterate. Lots of simulations, lots of adjustments, guided purely by the designer's experience, their gut feeling almost.
Sounds incredibly time-consuming. And maybe hit or miss. The paper mentions it can take weeks, needing constant back and forth. Designer, simulation tool, designer.
Exactly. And here's a really crucial limitation. The traditional methods, they might get you to a target frequency or, a deep signal response.
Which sounds good.
It is, but they often don't explicitly optimize for sensitivity. You might end up with a sensor that works at the right frequency, but it might not be the most sensitive one possible.
Why not?
Because directly targeting sensitivity in that manual iterative process is just complex. It's not usually the primary focus.
Plus, relying on human intuition, you're kind of limited, right? You probably stick to designs you already know, variations on a theme.
You do. And just trying tons of combinations, parameter sweeping, it gets computationally very expensive very quickly, especially for complex shapes.
Okay, so this is where the AI-driven, unsupervised approach comes in. It sounds much more powerful.
It really changes the game.
So how do they actually do it? What's the core idea here?
The central innovation is this unsupervised design methodology. Unsupervised means, well, once you give the AI the high-level specs like the frequency you want and a set of allowed building blocks,
Okay.
the whole design process just runs automatically. No human stepping in to tweak things halfway through. That's the unsupervised bit.
And these building blocks, what are they? Like basic shapes that AI can play with?
Precisely. Think of fundamental elements.
Yeah.
Circles, squares, resonators, straight lines called stubs, cutouts, or slots.
Right.
The AI can change the size of these blocks and, crucially, combine them using Boolean operations.
Like adding shapes or cutting one out of another.
To generate potentially very complex final geometries. The paper mentions using a specific material, too, RT5880 substrate.
Why that one?
It's a common choice for microwave circuits. It's stable, doesn't lose much signal energy at these high frequencies. important for performance.
So the AI isn't just picking old designs, it's actually building new ones from these pieces.
Yes, it's generative. And it controls this whole creative process using some pretty powerful AI optimization techniques.
Like what?
They use evolutionary algorithms, kind of inspired by natural selection for the big picture, the global search, and then gradient-based optimizers for the fine-tuning.
Ah, and the paper mentions a clever two-stage process for this.
Yes, that structure is key. It makes the whole thing manageable computationally.
Okay, let's break that down. First, they talk about parameterization. This sounds important. Instead of designing pixel by pixel,
Which would be millions of variables, totally impractical.
right, they represent the sensor's shape using just a small number of continuous parameters, only 16 mentioned in the paper.
16 numbers, and this is where the smart part is. These numbers control not just the sizes of the elements, but also whether certain elements are even used in the design or how they connect and combine.
So those 16 numbers can describe a huge variety of potential
A
sensors.
vast design space, yeah. But with only 16 knobs for the AI to turn, which is computationally feasible.
Okay, parameters define the possibilities. Then stage one, global search. Or they call it architecture evolution.
Right. The goal here is exploration, broad strokes. The AI, using that evolutionary algorithm, it's adjusting the architecture, the overall layout, and the dimensions all at the same time.
What's it looking for?
Trying to find designs that hit that target operating frequency and do it with a strong signal, a deep transmission notch. I mean, the sensor resonates well.
And getting the frequency right is priority one.
Primarily, yes.
Yeah.
That's the main goal of its objective function, the mathematical target it tries to optimize. But cleverly, for designs that are already getting close on frequency and show a strong signal, say below negative 20 decibels,
Okay.
it also starts considering sensitivity, even in this first stage. It nudges the search towards designs that are not just on frequency, but also potentially more sensitive.
And the algorithm adapts. It doesn't just search randomly.
No, it learns. Early on, it might make bigger changes, higher mutation rates, to explore really different ideas. Later, as it finds promising areas in the design space, it reduces that mutation rate to fine-tune those designs more carefully.
Makes sense. So stage one finds a good neighborhood, a promising architecture, and rough dimensions. Then you hit stage two, local tuning, focused on sensitivity enhancement.
Oh, now the goal shifts. You've got a solid structure from stage one. The aim now is explicitly maximize sensitivity.
How? Different tool.
Yes, here they use a gradient-based optimizer.
Yeah.
These are really efficient at fine-tuning when you're close to a good solution.
So stage one finds the best type of sensor shape, roughly, and stage two polishes it for peak sensitivity.
Got it. And the objective function in stage two reflects that. It's primarily maximizing sensitivity, but, and this is important, it includes a penalty term.
A penalty for what?
If the design starts drifting away from that target operating frequency found back in stage one, it keeps the frequency locked in while pushing sensitivity higher.
And crucially, because of that initial parameterization setup, both stages are working with the same 16 parameters.
Correct. Stage one finds a good combination and rough values for those parameters. Stage two then just tweaks those same parameters, maybe just slightly, to boost sensitivity without messing up the frequency.
That's quite elegant. Big changes in stage one, small refinements in stage two, all using the same control vector.
Exactly. And throughout both stages, every candidate design the AI proposes gets evaluated.
Using simulations.
Yes, using standard electromagnetic simulation software like CST Microwave Studio mentioned in the paper. They simulate the sensor empty or unloaded,
Right.
and then simulate it again with a known test material placed on it. Comparing those two simulations lets them calculate the sensitivity using their defined formula.
Right, measuring the frequency shift. And the speed is the kicker here. The paper says the whole unsupervised process, about 16 hours.
Roughly, yeah.
Yeah.
That includes something like 1,200 EM simulations for the global search and maybe up to 200 for the local tuning.
Compare that to weeks for a human designer. It's night and day.
It's a massive speed up in the design cycle.
Okay, so let's get to the results. The proof is in the pudding. What kind of sensors did this AI system actually cook up?
Well, they demonstrated it first by targeting different frequencies using simpler building blocks, just a square ring and a stub.
And did it work?
Yep. They successfully generated sensor designs for 3, 6, 9, 12, and 15 gigahertz, showed the expected trend. Higher frequency means smaller sensor size, and achieved pretty decent sensitivity too, around 7 to 10%.
Okay, solid baseline. But the really interesting part was when they let it use multiple building blocks, right, for more complex, high-performance sensors.
Exactly. Their high-performance sensors, labeled sensor 1 through 4 in the paper, really showed what the AI could do when given more freedom to combine elements.
And these hit higher sensitivity.
They did. Sensitivity exceeding 10%. Sensor 4, for example, reached a simulated sensitivity of 11.34%, operating up around 15 to 17 gigahertz.
That's a concrete number, a tangible output from the AI.
And importantly, they didn't just leave it at simulation. They actually built one.
A fabricated sensor 4.
Yes, and then they measured it experimentally. Real-world validation.
Okay, this is crucial. How did the physical sensor perform compared to the computer model?
So they measured the fabricated sensor 4. Its resonant frequency came out at 15.91 gigahertz. The simulation had predicted 15.42 gigahertz.
Ah, a slight difference, about half a gigahertz.
Yeah, 0.49 gigahertz, which is actually pretty common when you go from simulation to reality. It's usually chalked up to tiny imperfections in the manufacturing.
Like fabrication tolerances, the exact dimensions might be slightly off, or the material properties.
Exactly. Material properties, surface roughness, tiny things can shift the frequency a bit, but it's still very close.
Okay, so it works in the real world, close to the prediction.
Right.
How did they then make it useful for actually, sensing things, measuring materials?
They calibrated it. They built an inverse regression model. Basically, they trained a mathematical model. They measured the sensor's response, its frequency shift, when interacting with a bunch of known materials. Materials with different electrical properties, different permittivities, and different thicknesses.
And the model learns the relationship.
It learns to predict the material's properties based only on the sensor's measured frequency shift and the material's thickness.
Okay.
So you measure the frequency, the sample thickness, and the model tells you the permittivity. The paper notes, interestingly, that permittivity changes the frequency much more significantly than thickness does.
That makes sense. And was the calibration accurate? Could it reliably predict?
They tested it with separate validation samples, and yeah, it predicted the permittivity really well. The average error was only around 3%.
That's pretty good.
Very low error. Maximum was about 7%. So it confirms the sensor can reliably characterize materials over quite a wide range of permittivities, from about 2 up to over 10.
Okay, impressive accuracy. Now, the big question. How does this AI-designed sensor stack up against the competition? Against the best sensors designed the old way, the manual way, reported in other research.
Right, the benchmarking. This is where it gets really interesting. They took their measured sensitivity for the fabricated sensor 4.
Which was, what, again, slightly different from simulation?
Slightly lower due to real-world factors, but still very high. 10.69% measured sensitivity.
Okay, 10.69%. How does that compare?
They compared it against various state-of-the-art sensors from the scientific literature. These manually designed, published sensors typically had sensitivities ranging from maybe 5% up to around 9%.
So the AI sensor, even the real fabricated one, was more sensitive than these top-tier human-designed examples.
That's what the data shows. The AI-generated design, experimentally verified, achieved a sensitivity over 10%. Clearly outperforming those benchmark structures which clustered in that lower 5 to 9% range.
Wow. Okay, that really drives the point home. This unsupervised AI technique. It's not just faster, hours versus weeks.
Huge difference there.
And it's not just automated, needing no hand-holding after setup.
Right, fully automatic.
But it can actually explore the design space and find solutions that explicitly optimize for critical things like sensitivity. Maybe finding shapes or combinations a human wouldn't even think to try.
And leading to genuinely higher performance.
Yeah. It really shifts the engineer's job, doesn't it, from doing the laborious optimization
To defining the problem well, setting the right goals, and letting the AI handle the intensive search.
So what does this all mean for you listening? This deep dive really highlights a powerful shift happening in how complex things like these microwave sensors can be designed.
It's a new way of thinking about design.
By clearly defining what you want, a specific frequency, maximum sensitivity, you can basically unleash AI to explore possibilities far beyond what manual methods could realistically cover.
And do it much faster and potentially find better solutions.
You've heard how the system uses those basic building blocks, that clever two-stage optimization, evolving and then fine-tuning sensors that demonstrably outperform traditional ones. It's not just about sensors, really. It's a glimpse into a future where many complex engineering tasks might be tackled much more efficiently, more effectively.
By leveraging intelligent automation, augmenting human creativity and insight with AI's computational power.
Exactly. And here's something really interesting to think about, the final thought. The paper mentions future work,